So here's a problem from complex numbers. We have been asked to prove that if we have a triangle whose vertices are represented by the complex numbers z1, z2 and z3, that triangle will be an equilateral triangle if this property is satisfied. So this is what we have to prove. So we'll prove that by first assuming that this is true, and from there we'll show that if this is true, then the triangle with vertices this and this, that is z1, z2, z3, will be an equilateral triangle. So before we start that, we'll just have to remind ourselves of a few concepts regarding complex numbers. So first of all, complex numbers have both magnitude as well as direction. For example, a complex number z can be written as x plus iy, and the modulus of that complex number is square root of x squared plus y squared. And this complex number also has a certain argument, the angle it makes with the positive x-axis. If I express the complex number in polar form, I'll say that it's r times cos theta plus I sin theta. So here's a complex number which has a magnitude r and makes an angle theta with the positive x-axis. So a complex number has both magnitude as well as a direction. We won't say it has a direction, but we'll say that it has directional properties because it has a certain angle. So we can always treat a complex number like it's a vector. So suppose I have two complex numbers, z1 and z2. So I have two complex numbers, z1 and z2. The origin, say, is O. So let's call this point A, and let's call this point B. We can represent the vector OA by the complex number z1, and we can represent the vector OB by the complex number z2. So if I make the vector BA, by triangle law I can say that OB plus BA, that equals OA, and hence the vector BA is represented by the vector OA minus the vector OB. So BA is represented by the complex number z1 minus z2. Hence the length BA, which is also the magnitude of the vector BA, can be represented by the magnitude of the complex number z1 minus z2. Similarly, the angle the vector BA will make with the x-axis, let this be that angle theta, the angle can be represented by the argument of the complex number z1 minus z2. So what we are saying here is the vector BA is represented by the complex number z1 minus z2, and the length of BA therefore becomes the magnitude of the vector BA, or the magnitude of the complex number z1 minus z2, and the angle theta then becomes the argument of the vector the argument of the complex number z1 minus z2. So if we extend this idea a little further, we can say that let us do this with three complex numbers now. So I have a complex number Z1 here, I have a complex number Z2 say here, and another complex number Z3 denoted by this point here. This is obviously the Argand plane. So let me draw a vector this way, another vector that way, and let me extend these lines. Let's say that this angle say is alpha, this angle say is beta, and let us say that this angle is theta, and say we are required to find the angle theta. So what will be the complex number expression in terms of argument for this angle theta? So first of all, we can say that the argument of the complex number Z2 minus Z1, that is this vector, is represented by the angle alpha. The argument of the complex number Z3 minus Z1 is represented by the angle beta. And let us see, this angle is 180 minus alpha. So this angle will be how much? 180 minus 180 minus alpha plus beta, because the sum of three angles of a triangle is 180 degrees, so that becomes alpha minus beta, and because these two angles are vertically opposite, theta will be represented by alpha minus beta. So theta being equal to alpha minus beta, we can say that theta is argument of Z2 minus Z1 minus argument of Z3 minus Z1. And we know that the arguments of complex numbers have a property that argument of say Z2 over Z1, this equals argument of Z2 minus argument of Z1. So using this property, here we can say that this becomes, theta becomes, let me just do it over here because of lack of space, theta becomes argument of Z2 minus Z1 divided by Z3 minus Z1. So from here we have come here. So this is an important thing to remember if we have to solve this problem. Let me remind you of what this problem is. The problem they have asked us is that if we have a triangle whose three vertices have been represented by the complex numbers Z1, Z2 and Z3, we'll have to show that this triangle is an equilateral triangle given that this condition is true. So let us do that on the next page. So this is what we have been given: Z1 squared plus Z2 squared plus Z3 squared minus Z1 Z2 minus Z2 Z3 minus Z3 Z1 equals to 0. Z1, Z2, Z3 all being complex numbers. So let me manipulate this a little bit. I'll keep all the Z1 terms on one side and take all the other terms to the other side. So we have Z1 squared minus Z1 Z2 minus Z3 Z1. This is equals to minus Z2 squared minus Z3 squared, and I have a plus Z2 Z3. I'll add z2 z3 to both sides, which will give me z1 squared minus z1 z2 minus z3 z1 plus z2 z3, and on this side I'll get minus z2 minus z3 whole square. I'm adding another z2 z3, so I get a 2 z2 z3. If I take minus common within the brackets, I'll get z2 squared plus z3 squared minus 2 z2 z3, which is this. So from these two terms, I'll take z1 common. I get z1 minus z2. From these two terms, I have a minus z3 common, and I get z1 minus z2, and this is equals to minus z2 minus z3 all squared. So after manipulation, I get z1 minus z3 times z1 minus z2 equals, let me write this in a slightly different way. I'll write this as z2 minus z3 times z2 minus z3, but not quite, z3 minus z2, because of this negative sign. So this can be written as z1 minus z2 divided by z3 minus z2. This equals z2 minus z3 divided by z1 minus z1 minus z3. Yeah. So here's a complex number. This whole thing is a complex number. This whole thing is a complex number. They are equal, so their magnitudes are equal and their arguments are also equal. So equating their arguments, we can say that argument of z1 minus z2 divided by z3 minus z2, this equals the argument of z2 minus z3 divided by z1 minus z3. So let us make a triangle. Say this point is z1, this is z2, and this is z3. z1 minus z2 is actually this vector, and z3 minus z2 is this vector. So argument of z1 minus z2 divided by z3 minus z2, it means we are talking about this angle. Similarly, I'll just make, okay, z2 minus z3 is this vector here, and z1 minus z3 is that vector. So argument of z2 minus z3 divided by z1 minus z3 means we are talking about this angle, and we are saying that these two angles are equal, which means that these two sides are equal. So this side and this side, they are equal. So from there we can say that this implies, because these two angles are equal, their opposite sides are equal, so we can say that mod of z1 minus z3 equals the mod of z1 minus z2. So here's an interesting little result that we get. Okay, I think I'll have to use another page. Okay, so what we had originally got was argument of z1 minus z2 divided by z3 minus z2 equals the argument of Z2 minus Z3 divided by Z1 minus Z3. From there we got another result, and that result was mod of Z1 minus Z2 equals the mod of Z1 minus Z3. But for now we'll use this. And why were these arguments equal? These arguments were equal because these complex numbers themselves were equal. So this and this are equal. So because these complex numbers are equal, their moduli are also equal. So we can say that the mod of this equals the mod of this, but we know that the mod of Z1 over Z2 equals the mod of Z1 over the mod of Z2. So we can say that mod of Z1 minus Z2 divided by the mod of Z3 minus Z2 equals the mod of Z2 minus Z3 divided by the mod of Z1 minus Z3. So if I cross multiply, I can say that mod of Z2 minus Z3 whole squared, I'm actually multiplying these two terms, and because we are within mod, it doesn't matter I write Z3 minus Z2 or Z2 minus Z3. This equals mod of Z1 minus Z2 times the mod of Z1 minus Z3. But look, here we have mod of Z1 minus Z2 equals the mod of Z1 minus Z3. So in place of Z1 minus Z2 mod, I can write Z1 minus Z3 mod. So we get mod of Z2 minus Z3 squared equals the mod of Z1 minus Z3 squared, which gives us mod of Z2 minus Z3 equals the mod of Z1 minus Z3. Since we are dealing with mod, there is no question of a negative square root. Let me go back to the triangle again. I had my Z1 over here, and let me see. Yeah, I had my Z2 over here and my Z3 over here. I have already shown that these two angles are equal and these two sides have been shown to be equal. So let us see what this equation tells us. Mod of Z2 minus Z3. So mod of Z2 minus Z3 is actually this side. This is mod of Z2 minus Z3, and mod of Z1 minus Z3 is actually this side. We have now shown that these two sides are equal, and these two sides were already shown to be equal. So these three sides are now equal. This shows that this is an equilateral triangle. So if this is A, this is B, this is C, we have now shown that AB equals to BC equals to AC. So our proof is done. Triangle ABC is an equilateral triangle.